see. Oh, there it goes. As usual, the recording will be available online after the meeting in case you missed any part of it or want to review or share with any colleagues. And I don't know if Phoebe is on the meeting today. If Phoebe or one of her colleagues is on, they will be taking notes for her project, and you can find out more about that at the link that I've got up on the screen here. So I'm going to let Elizabeth introduce Josh, who will be our first speaker. And then we'll hear later from Tushar from Microsoft to talk about the FarmBeats Research Preview pipeline. And then Shiang and Gloire from Cornell University are going to talk about a project they did over the summer and the continued work on that project. So Elizabeth, go ahead.
Fantastic. Thank you, Stacy, and welcome everyone to the FarmBeats User Community Workshop. Josh is here joining us as a special guest today. He is the founder and CEO of Ag Analytics. And Josh, good morning, good afternoon. Do you have slides you'd like to share with the group, or do you want to put those up while we're introducing you? Josh and our team met several years ago when he was a faculty member at Cornell in the economics department. Ag Analytics is a spin-out from Cornell and integrates all kinds of different ag data, and the platform itself is built on Azure, so we've had a partnership supporting some of the Azure behind Ag Analytics for the last couple of years. So Josh, we've invited Josh to give a short overview of what Ag Analytics is and talk a little bit about some of the university partnerships that they have created, which includes some of the universities we have represented in our FarmBeats community, including NC State and Purdue. So Josh, I'll turn it over to you. Welcome.
Yeah, can you hear me okay?
Yep.
Absolutely. So thanks for having me, really appreciate it. So yeah, as Elizabeth mentioned, I'll just give you a quick background on some of the things that we do in the university partnerships that we've been supporting, along with Microsoft has actually given some grants to our partners as well. So yeah, it's a quick background on the company. Started this company in 2008. I actually went on leave for a year, and then now I do this full time. So here's we have 13 employees currently. We have a couple locations, one in Indiana and one in New York. This map over here kind of shows a footprint of our users, so to give you an idea of where our users are kind of in the world. So I would say most of it is predominantly in the US. And by the way, the users on this map are, these would be users that have integrated their precision data, which I'll get into in a minute if you're not familiar with the precision ag systems. But in total, we house something on the order of 350 million acre years of high resolution precision data that we manage for our clients collectively. So it's quite a bit. We also house, in conjunction with Azure, a few hundred terabytes of satellite and other data that we make available in various forms to folks. So skip ahead a little bit on this in terms of our advisory board and so forth. But so just to kind of back up, you know, and by the way, I come from an ag economics background, so doing a lot of work in insurance and production economics modeling, where typically we're trying to get data that we can fit models with on usually kind of fairly large scale. So the more of it we can get and the higher resolution, the better. So, you know, what we would typically find was it was really hard to get yield data and other detailed data with it about management, like what fertilizers they were using and where they were planting it. And a lot of times you can only get county level data. Sometimes when we were working with insurance companies, we could get, you know, maybe farm level data, but we wouldn't know exactly where the fields were. And we certainly weren't getting subfield data. So the kernel of this really started where we did an integration with John Deere, and I'll talk about the integrations we have now. We pretty much cover the whole market now. But basically allowing our growers to connect their equipment to access the precision data for research purposes and extension purposes. And we've, you know, subsequently built some tools around that. But one of our original motivations was really for doing yield modeling and other types of modeling that would require those data. So for example, a lot of my research sort of revolves around collating those data with satellite data, and then using, statistics and machine learning to estimate models. So after I kind of built this up, kind of realized that, a couple of things. One, it was really hard. It was really expensive. In fact, it became a company. What sounded like a simple idea, kind of to really do it for real and to scale it, and to have the proper engineering to actually, do it on any meaningful scale is really a whole effort in and of itself. But what I kind of looked back on and thought was like, if I had access to a system like that where I could just send my growers, they could integrate, it would do all the processing to, match it with satellite data, convert it into shape files and rasters and stack it and pack it into forms that I could just start doing modeling immediately. Like that's really what I had wanted. Of course, we built that out quite a ways since, but so our thinking here was, can we spin up some partnerships? And by the way, we do this for free. We don't charge our university partners. We view these as collaborations. If it's private companies that want to leverage our system like this, we certainly charge them for that. But for the universities, because I kind of have a university background, the idea is to approach these like collaborations, and I'll talk about how they work. But in a nutshell, what we do is set up your own portal for you that allows your growers to come. We have an agreement that we've worked out and we've vetted with. We have 7 university partners now that basically the grower can come in like a minute. They can integrate their John Deere, Climate, CNH, whatever equipment they have, or they can upload files manually. We also support manual conversion of like something like 40 different file types from Precision Data. And then we do all the processing and basically provision to you a couple things. So what we currently do is we basically set up for you like your own database and your own blob storage on Azure where you can access the data. And then we also provide a lot of different APIs and stuff like that to make your research earlier. So literally what took me, I did the first kind of big model with a couple million acres for yield models that we were working on back in 2017. It took me about a year to do all the work to spin that up and collect the data. And so literally you could, once your producers integrate, which takes like 30 seconds, you could literally be doing modeling the next day. So I'll skip ahead on some of this. The punchline is we support all the major systems. They're all a little bit different in terms of like the data that, like how their integrations work and the data they send. And it's thousands of hours of engineering to get that stuff actually to work and to harmonize. So we kind of take care of all that. In case I'm talking like a different language, so when we say precision data, typically what we're talking about is 4 classes of files, at least what we typically support right now. And that would be seeding, application, harvest, and tillage. So these would be sub-field, sub-meter resolution GIS data that are collected, and they're very detailed. And so they're good ground truthing data. So if you want to do any kind of yield modeling, or if you're trying to do models to say predict whether someone tilled the land or not, or so on and so forth, these are really good data for that. So basically what they do is they come in as kind of raw sensor data. We organize them, we build shape files out of them that then are kind of like you see here, where it's sort of features on the field of the coverage. And then we have a process where we then automatically rasterize them, reproject satellite data and so forth, and then kind of reorganize them into a form that you can just load in and start modeling. We've kind of arranged it in such a way that it makes it easy to work with. So we put all that data in secure blob storage for our university partners. And then we have a kind of a metadata database that we provision. I can't get into all the details here, but we also have a lot of other API connections that are useful, which are, again, ones that I've sort of built in the process of my research and also the products that we now build that are kind of like utility data sets and services that you would need. So for example, to do things like, calculate different types of elevation indexes and grab from other data sets and so on and so forth. But yeah, here's just one example of kind of the types of models that you can do, which is really actually, quite fun in my opinion. And this is just an example. There's other areas as well, but I think, what we found is that when you can really scale this out, to the kind of millions of acres sort of scale, you can answer these questions in a completely different way. One of the other value adds that we have, for example, one of the things we've done for our own yield modeling is we typically want to be able to break down like what's actually going on in the field. So we have something like 100,000 different product names and traits, cultivars in our databases that come in with the data. And we know, down to the meter, like what variety was planted, what was the tank mix. But what you start finding when you get into it is that the data, there's like thousands of varieties. There might be misspellings or alternative spellings. There's lots of different product names, whereas really what you want to do is you want to get it down into like pounds of nitrogen, or do they have this trait or not? Or so anyways, we've built up and done tons of data collection and built, lots of processing to fluidly incorporate this. So like this stuff, trust me, would take you and your grad students hundreds of hours to even scratch the surface. So we've really industrialized it, built it out so we can, ask all sorts of questions in our modeling that are very detailed, like what if they, had this trait or not? What if they were using, this type of input versus that kind of input, et cetera. So really, there's just a multitude of things you can do. I mean, I really think it's endless. I think, in our experience so far with our partners, which I can kind of show you who are our partners so far. And Elizabeth, I'll wrap up here in about 1 minute. These are just starting. I mean, we signed the first one, I think a year ago, maybe, or less than a year. And they're sort of getting up to speed on how to use the data. And by the way, we work with our partners a lot in terms of like really sitting down and explaining how the data were processed, what they are. Some people have varying degrees of sort of familiarity with that. Yeah, it's been really fun so far. And we're having some papers that are getting finished up that are going to start coming out. And the last thing I'll mention is, just so that one of the harder things of this that we solved was figuring out how to do the governance with the university. So we made it really simple at the end. Basically what happens is the data from the farmers is confidential, okay? So the farmers don't want you releasing that data publicly. You can use it for research. You can publish all the papers you want. You just can't release the raw source data of the growers, which is kind of not uncommon, by the way, as you all know, in academia, despite some open data initiatives. The reality is, a lot of times there's confidential data sets, or there's PII in data sets that's not disclosed. So we've got all the right language for that. We haven't run into any cases where it's restricted anyone from doing anything they wanted to do. And secondly, with the IP, again, we view these as collaborations. We're not trying to do IP capture. So basically, the easiest way to do it was just to say, make it all open source. So basically anything you develop is open source. You can do whatever you want with it. We don't make any claim to your IP, and the university doesn't make any claim to our IP. So it's actually worked out quite well in terms of how those have shaped up. So if this is of interest to you, feel free to get in touch. And it can be, individuals or groups. We've done both. And so, yeah, looking forward for those of you that would find this, supplemental to help your research, happy to talk and explore possible collaborations together. So thank you.
That's great. Thank you, Josh. So I just wanted to open it up to questions from the community, from the group that we have here. And then I think we may have Purdue, and I'm not sure if we have NC State on, but I don't know if anyone from those universities has had any direct experience with the Ag Analytics partnership. It'd be great to hear from you as well. So it looks like Hakeem has his hand up, very civilized. Hakeem.
Hi, Josh, thank you. I had a question about.
Oh, Hakeem, we're having trouble hearing you.
Can you hear me?
Yes.
Okay. I said, Josh, thank you. I appreciate that. It was great. I had a question about the confidentiality. I think it requires encryption. So do you have suggested ways of maintaining encryption? One of the things that is kind of a stumbling block, actually wasn't a stumbling block, but just requires some follow-up. I think github.com stores things encrypted, but the key, I think, is just having some general recommendations of how to maintain that confidentiality to the agreement.
Yeah, that's a good question. So, I mean, I think of it as a couple of different things. So first of all, all of the databases that we create for our partners and put in Azure, I mean, when you talk to them across the line, it's all encrypted, right? I mean, you can't connect to it without it being encrypted. The databases at rest are also encrypted, et cetera. So that's not really the issue. What we also do is we also strip some of the information out so that it just makes it easy, because you probably don't care who they are, but we have like org IDs, but you can see where the data are. So those data that are location specific should not be, made public. Really though, at that point, we're not using like fancy blockchain or anything like that. Basically, once you access the database, you can either process it on your own VMs or resources, on site, or on Azure data centers, or you can download data and work with it locally. I mean, once you have the data, yeah, it's your responsibility, and basically, we kind of have protocols that are outlined in the contract that are very basic, like, the computers, if you download it locally, should have, BitLocker installed. You won't be able to connect to the resources without using, TSL and SSL and so forth even. But we pretty much use all of the resources that Azure provides in that sense. But once you have the data and you open it and you're working with it in MATLAB or whatever, I mean, you're under standard confidentiality restrictions at that point, but you can absolutely see the data you're working with. Yeah. So.
Thank you.
All right.
Yeah.
Any other questions for Josh?
In a while.
All right. Well, thank you so much, Josh. And if anyone has any questions or wants to learn more about ag analytics, Josh, can they reach out? Is there a way to reach out to you or someone on your team?
Yeah, you can either just email me. My email should be in that invite that you sent out, Elizabeth, or if you go to our website, just search for Ag Analytics and you'll see a contact form that has also email on that site. So josh@ag-analytics.org or josh@analytics.ag. So.
Perfect. Thank you so much.
Thanks.
All right.
With your permission, if you have the presentation, if you'd like to share that with the group, you can send it to me and I'll post it up on our team site, and maybe you have contact information in the presentation. It'd be easier for them to get a hold of that way.
Absolutely. I'll send that along to you. Thank you.
Perfect. Thank you. Okay, next we're going to hear from Tushar. He's a software engineer on Ranveer's team working with FarmBeats and specializing in the Research Preview product. And so he was going to share with us today the pipeline for Research Preview. Just for those of you that are using the Research Preview version of FarmBeats and are just needing a little bit extra help with the system components or communication protocol, he's going to go through those topics, and then we'll leave some time for questions at the end. Tushar?
Thank you, Stacy, for the floor. So actually, I think many of us here already have worked together on FarmBeats. So today I'm gonna give an overview of end-to-end FarmBeats Research Preview pipeline, starting from the ground sensor box to the cloud. And I know many of you are working on several interesting problems where FarmBeats pipeline could contribute a lot and vice versa. So I hope this overview will help you in understanding those opportunities from the technical design perspective. Let's get started with the FarmBeats deployment topology. Here we will talk from the perspective of ground sensor. So as you can see, we have multiple sensor boxes deployed in the field, and these sensor boxes collect sensor data in the field and sends it to the gateway. So the communication between the gateway and sensor boxes could be over LoRa or TB whitespace. Both are wireless technologies. And on the gateway side, we have a radio to communicate with the sensor boxes. It just works like a transparent relay. Whatever it receives passes to the sub-edge and the other way around. So sub-edge is basically a single board computer like Raspberry Pi or Intel UP board, but you can also use a laptop or your personal computer as the sub-edge. So once the data is in the sub-edge, it then does some initial processing and forwards it to the Azure. So let's have a look what we have in the sensor boxes. So with this sensor box, actually we can support 4 analog sensors in 11 RS485 sensor, which is basically digital sensors. We also have 3 onboard sensors. So analog and RS485, those are all external sensors. Like you can come up with your own sensors here. And for the power backup, we have the battery, solar, or adapter, whatever you want to use. And for the communication between the sensor box and the gateway, this box can support LoRa, TV white space, or even the Bluetooth technology. And we have some local storage, like several kilobytes, to store the configuration metadata, or sometimes the sensor data, like if there is any communication outage. And also we have a user debug interface to debug the sensor box. So, and on the gateway side, we have the main component is the sub edge. Here you can see we have an Intel upboard as the sub edge. It has the Windows IoT Core OS, and it's running our own FarmBeats UWP app. So for the communication with the sensor boxes, we have the LoRa radio here, but you can replace it with the TV white space radio. And for the backhaul connectivity, like to connect to the cloud, you can use LAN or Wi-Fi. So we got an idea of the infrastructure. Now let's move on to the data pipeline. So I would like to start with the communication between gateway and the sensor box, as the sensor box is the primary source of our data. So the sensor box collects the sensor data on a regular interval and sends it to the gateway. And so basically what we have in our data packet. So these are the information that we embed in our sensor data packet. So starting with the serial number. So the serial number is basically the unique sensor box serial number. Then we have the packet type. So the packet type is to distinguish between different packets, like acknowledgement, control packet, or data packet, whatever. And then we have the timestamp. So timestamp is basically the sensor data collection time. So it keeps you in synchronization. Then comes the problem, like is basically like in some cases your sensor data might be too long to send in one single data packet. So then what we do, we actually fragment the sensor data in multiple chunks, and we send those chunks. So basically, this is the kind of fragmentation. So in the data packet, we mentioned that how many fragments the gateway is going to get from this particular sensor box. And then we have the fragmenting index, the index of the fragment, which is embedded in this particular data packet. Because like we send different fragments in different data packets. So you have to mention that what fragment you have sent. So then comes the sensor data. So what we have in the sensor data is something like this. It's basically we have the sensor information followed by the sensor value. So the sensor information is basically some metadata, like say sensor type, sensor ID, and whether the sensor value is human interpretable or raw, all these kinds of information. And then we have the sensor value. So basically the sensor data is organized in a way we call it like channel-based organization. So it's pretty simple idea. It's basically on channel 0 you have the first sensor, and on the channel 1 you have the second sensor, and so on. So this helps us in organizing the data in the cloud. I'll show you how to do that. So now once the data packet is received in the gateway processes the data and prepares an acknowledgement as a response. And that ACK is sent back to the sensor box. And what we have in the ACK is basically the serial number. So you know, like whenever you are sending the ACK, like many sensor boxes can listen to that ACK, but it needs to know whether it is the ACK was intended for that particular sensor box or not. Then we have the packet type. Packet type, as I said, is to distinguish between data packet and acknowledgement packet. Then we have the timestamp. So this is crucial actually. So the timestamp, this timestamp is being sent from the gateway, and gateway is connected to the internet. So it has the updated timestamp. So what we do actually, like whenever the sensor box receives an acknowledgement, it actually updates its timestamp from the acknowledgement. Then we have the index for the last fragment that the gateway received, so that the sensor box can track what fragments have already been received on the gateway side. And finally, we piggyback some config information. So like this config information is to configure the sensor box, like for example, the data interval. So like after receiving the ACK, the sensor box checks whether there is any more fragment to send. If it has, it sends it to the gateway. So this way it sends all the fragments. Now the data is in the subpage. Now let's see what happens next. So as I mentioned, in the gateway, we have a subpage, which is basically running the FarmBeats UWP app. This app actually controls all the like earlier mentioned protocol and further data processing. So in the subpage app, we first merge all the fragments and we extract the sensor ID and corresponding info. And we do some trivial checks whether the data is correct or not. And then we organize the sensor data, like basically it's a typical serialization. And then we add a tag, like here we add telemetry tag for the sensor data. So why do we add tag? Basically from the subpage, we send several types of information like subpage, health data, or like image data, audio data. So different types of data stream is sent from the subpage. So in that case, to distinguish between these kinds of data stream, we actually use the tag. So for the sensor data, we use the telemetry tag here. Like I will tell you where the tag is used. So then we save it in the local storage. And once we have the internet available, we send it to the IoT hub from the local storage. So now data is in the IoT hub. So when the data is in the IoT hub, it first passes through a message router. So it actually, the message router actually forwards the message to different endpoints based on the message tag, as I said earlier. So like for image, it sends it to the image endpoint. Now endpoint is nothing, like in Azure, most of the cases endpoint is a permanent or the temporary storage. Like for image endpoint, you can use the blob storage. But here our focus is on the telemetry endpoint. And for the telemetry endpoint, we use the service bus queue. So the sensor data goes to the service bus queue. Now, whenever we have the data in the service bus queue, it triggers an Azure function. So this is our own Azure function. And the Azure function pops the data from the queue and does the final processing. So basically, the final processing is converting the data to the human interpretable value, because like data could be the sensor value could be raw, like you might not be able to make any sense of that sensor data. So what we do, we actually make it human interpretable, and also we do some organization in a sense based on the sensor queue. Like I will come to this concept later, the sensor queue, but it is predefined in the cloud. So then once we have this organized data and human interpretable, we save it in the Azure storage table. And from the Azure storage table, our web app extracts the data and shows it in the dashboard of FarmBeats Azure website. So here you can see a snapshot of our FarmBeats dashboard. So you can see all different types of sensor data here. Now let's talk about the due concept of sensor queue. So here the idea is basically selecting the sensor based on the need, because we might not need data from all the sensors in a sensor box, like all the 15 sensors or 18 sensors. You might not need all the sensors data. So for example, someone might be interested in monitoring soil moisture, soil temperature, or ambient temperature. On the other hand, someone might be interested in wind sensors. So it's like making a fruit basket as you want for each sensor box. So there are several advantages of this thing. The first thing is obviously you can customize what sensor data you want. The second thing is basically it keeps the option open for adding new types of sensor. And obviously it saves your power and bandwidth usage. Like if you want to send the data of all the 18 sensors, although you need only 3 of those, it's going to drain your battery, and also it's going to use your network bandwidth. So you can actually configure the SKU in the dashboard, like which is on our FarmBeats website. So you can select the predefined SKU, and also you can actually configure the SKU as you want. Like you can select the mean, max value, or default value, and also you can select the channel name. So the channel, here you can see the channel number is mentioned here. So as I talked earlier, so this is how the data is organized in the sensor box. Like when a data packet is sent from the sensor box to the gateway, the sensor box follows this order. So basically, whenever we have this SKU configuration, we save it in the Azure storage table. And as I said earlier, the Azure Function app uses that information to actually organize the data and make it human interpretable. So I think you also got an overview of the end-to-end system. So like for the time limitation, I didn't go deeper, but feel free to reach out to me if you need any further details. And thank you all for your patience. Thank you.
Thanks, Tushar. Does anyone have any questions for him about Research Preview or data integration? It looks like Gloire, do you have your hand up?
Yeah. Hey, Tushar. It's pretty cool to hear about the full pipeline.
Hey.
I had.
Hey.
So on the sensor box is a few kilobytes that you reserve for in case of an outage. What about on the sub edge when you're doing that file queue? Because I've seen it in action where the internet goes out, but then the data eventually gets to Azure. Like, does it have access to the entire storage of the sub edge in case of an outage? Or do you have a cap on how much of the storage can you use on the sub edge?
So actually, it's a trade-off, like how much storage you want to allocate. So basically, you can just change that. Like if you are not running anything else in the sub-edge, so sometimes you might want to run some other applications or some FTP server to receive the drone imagery or like even some videos. So in that case, obviously there is a cap depending on the storage available in your system, but you can configure that. Always.
Gotcha. Thanks.
Hi, can you hear me? This is Shamali.
Yes.
Yeah.
Okay, good. So this is actually my first time joining this FarmBeats community workshop. I had a little bit of inertia because, tons of projects as an assistant professor, but this is on my priority 2021. So yay, this is perfect, getting an overview of FarmBeats. So if we wanted to start using some of the FarmBeats equipment for our data pipeline, is this, I remember Ranbir mentioned there are some toy stuff that can be sent out to universities to start using some of the Azure pipeline and everything. So what is like a way to get started with your kit? So I'm used to the Azure cloud services. We've used it for various other purposes. We also have data being collected. We basically have InDesign nodes. They are deployed in the farms. So I want to know what is the way to get started with the FarmBeats kit. So I think that Tushar, the pipeline that he showed is very helpful, but actually in a tactile manner, what are the first steps to take to get started with it?
I think Stacy would be the right person to answer that.
And I think you're at Purdue, aren't you?
Mm-hmm. Yeah.
Yeah, and so we've been working a lot with your folks to get your system up and running. And maybe we can set up some time individually to work on what your specific questions are and getting things up and going.
Yeah. So this is a new project, actually. So the one that Dennis and everyone is doing, I'm familiar with that. So our project is a new NSF project. It's a National Science Foundation project, and it's actually starting this February. One of the things that we are looking to do is not only have this analytics going, but also have secure agro-analytics. So actually the topic of the project, it is basically securing the agro-analytics pipeline from end to end. And Ranbir is actually a collaborator. He wrote a fantastic letter of collaboration. And one of the things that we want to do, both from the engagement side, on the education side, how do we use FarmBeats as the data pipeline? And again, on the research side, we have these sensor data sets coming. How do we actually tap into FarmBeats to, to have the end-to-end pipeline and then use our algorithms to have security and everything in terms of enhancement of the pipeline. So the things that we do mostly for the data, I think our lab is a more algorithmic lab. So we are a 2-year-old lab, and we do a lot of object detection. So we are starting to buy drones, and we have embedded devices. So we basically want to see how to quickly tap into the Azure and FarmBeats pipeline to be just as of like yesterday, we placed orders for new drones. So we'll have Mavics and stuff to start using in a portion, an acre. So now would be a great time to see which is a good pipeline to sync with. So two things, I think, on the research side and then on the education side. So both of the things would be something we want to explore. So using the FarmBeats pipeline and then actually using it for our toy data sets.
Excellent. All right. Well, let me touch base with you after the meeting, and we can find a good time for us to talk and sync and figure out what the best next steps are to get you going quickly.
Yeah, and this was also my way to say hi. You know, this is this has been on my calendar. Cool.
All right. Any other questions for Tushar on today's presentation? All right, well, let's jump in then. We've got actually Shiang and Gloire from Cornell University. They're PhD students, and they've been working on software-defined farm, precision agriculture, and then a supporting decision engine for the software-defined farm. And I don't know if we'll have time to talk about both things today, but I will let Shiang and Gloire decide how they want to proceed. And if we don't have time to finish everything today, we can always bring them back again in February to talk a little bit more about their project. So I'll hand it to Shiang and Gloire.
Thanks, Stacy. Great to be here, and thanks for giving us also the opportunity to present. So I think we'll have time to present both of these topics and maybe like a 5-minute Q&A at the very end. And so with that, I'll jump right ahead. So as Stacy mentioned, we're going to explain kind of the software-defined farm, that concept, and the subsequent decision engine, which was a lot of collaboration jointly between us, our team, and Microsoft, so Gloire and myself, and we'll get into it. So what we're thinking about the motivation for this was, we understand that water consumption is a problem because agriculture uses 70% of that globally, and we understand that one almond requires not just, but 1.1 gallons of water. And so we need to use precision irrigation, which has been proven to save up to 35% of water in agriculture. And so here's the problem. When we understood our research, we understood that a lot of the limitations we faced closely resembles that of farmers currently in agriculture. So first, we understand that there's a limited budget for farmers. They spend about $50 per month on technology investments. Second, we know that we need a lot of reliable data to really have impactful insights for each particular farmer. And then lastly, we understood that scalability is also an issue. So what we're doing in the lab a lot of times does not translate into the field. And we understood that very well during this past summer. And so, again, this past summer, we had an awesome opportunity to deploy this technology to the fields at the Cornell apple orchards, which we utilize unique sensors, such as from the Stroop group, the microtensiometer, which is to understand water stress. And this was really awesome for us because it was a great opportunity to kind of test collaborations from different groups. And at the very end, we had 4 months of successful deployments running a closed-loop irrigation system that showcased our digital twins. And it's actually still running today. That's awesome to see. And so you might be wondering, what is a software-defined farm? Well, it's an open source, layered, and adaptable approach for decision support on the farm. And it integrates automation, artificial intelligence, and the cloud to optimize farming and increase profitability for a particular farmer. So now I'll take you to the deployment location. So first, I'll show you kind of a broad look of New York, then zooming into the Ithaca area, and now into the apple orchard. And you see our field here and the shed, which we'll describe actually in this video demo. So in this video demo, we'll take you through to the actual field where we have 4 trees. It's currently out of season, so we know that there's no real leaves or apples or really precise data, but this is to show you what it looks like. So now we have Gloire, who's looking at our sensor box just to make sure data is flowing correctly through the sub-edge and into the cloud. And you can see that there's a couple sensors here placed on the tree. And next we can zoom in on another tree where we have this microtensitometer, which we described as understanding water stress, placed in the tree for show here. And we can see a soil moisture sensor, and at the very end we will see a wind director sensor, which we ad hoc kind of put together, and it looks pretty cool though, so we kind of kept it this way. And then very lastly, we'll see just a last of our trees, which is not set up with any sensors. And then after this, we'll zoom in to the water irrigation valve, which water flows directly to the tree when we understand that a tree is in fact thirsty. And then lastly, we'll show you the shed. The shed is where we keep our sub-edge device, which Tusher described earlier, which is porting data from the trees to the sub-edge to the cloud through a Wi-Fi hotspot. And now I'll hand it over to Gloire to kind of explain the data.
Thank you, Shang. So to start with our system, we had 2 disjoint data sets here, where one of them was a wired setup early in the summer, and was streaming the data to the Raspberry Pi and sending the data to the ThingsBoard cloud. And then the next one is what we just showed in the video, is a wireless system sending the data to the sub-edge and into the full pipeline that Tusher just described in the Azure cloud with the service bus, and then triggers an Azure function, and then it finally displays in the dashboard. So what we're trying to do is to try to unify the wired and the wireless setup so we can remove that one cloud on the right hand and bring it all together so we can pull in some of that data from our sensors, the FarmBeats sensor box sensors that we have, and decide on whether irrigation should be triggered at the farm and send that message back to the farm to trigger the relay. So I'll show an end-to-end demo of the system. So as I've described, we have 2 systems. One of them is wired and another is wireless, and we're trying to bring them together and streaming that data to the Azure cloud. And in the cloud, so the Raspberry Pi, as you can see on the mouse, we take the data, stream it from the Raspberry Pi to the cloud. And in the cloud, we trigger the irrigation decision, send it back to the relay valve that then turns on the water. That's the end-to-end system. So on the top left screen, what we have is the streaming the data from the Raspberry Pi to the cloud. And then the second screen is going to be in the cloud. We're listening for messages coming in from the farm. And then the top right screen is going to be at the farm. We're listening for messages coming back from the cloud on whether to trigger. So the first one I just started is listening messages coming from the farm. And then at the farm, we listen for messages coming from the cloud. So then now we have those two of those set up, then we'll start streaming the messages then from the Raspberry Pi going to the cloud. As you can see, once it goes to the cloud, in the cloud, it triggers a water stress signal. And then we pull in weather forecast for the next 7 days. Is it going to rain? If it's not, then we need to send a message back. And in doing so, we have to first bring in the data from the FarmBeats system. We pull it in, we can see the soil moisture sensor and the light intensity sensors, and then we put together an outgoing message back to the farm, which says when was the message triggered, which valves should we turn on, and when the message was triggered, what the water deficit was in the tree. And then that together, then we store the message for future reference and analysis in an Azure table for future, any future research and other purposes. So that shows the end-to-end system from the Raspberry Pi to the cloud and back to the farm. And that will move on to the next slide. So now that we have the full system, what we'd like to do in the future for this spring is we're going to then move to start using a long-range LoRa antenna. And we've also ordered some TV white space radios that we can then switch between LoRa and TV white space, as Tusher described. And then also we're collaborating with some other people who are interested in bringing this technology into a greenhouse setting with a controlled environment agriculture.
Awesome. So now we'll describe this decision engine, which is going to help farmers understand which network they should connect to and how they should understand these decisions that they need to make to deploy an instance of the software-defined farm, which you described earlier. So there's three technology components. So first, you understand the network. So which is the optimal network for their actual farm, wherever they may be. Second, the device topology. Where should they place these sensors to have the optimal coverage for their farm? And lastly, we understand the return on investments. What are they going to make from the technology that they just bought? And so now we pass it back to Gloire.
Thank you. So now we're going to describe the idea of a software-defined spectrum. So for a minute, just imagine with me, you have Cornell is a field. You have 8 fields on it, and the 8th one is not connected, but the other 7 are connected to wireless ISP. And what you can do is you can just connect the 8th device using LoRa, like we're doing at the moment, and send that message into a network that has connectivity to Azure and send that data. Another one is, instead of reliability, what if you want the highest coverage? Then you can also use TV white space to send it to a TV white space gateway. Yet another one, let's say you want to have the highest capacity, you want more to send drone data, like drone images, then you can also plug it into the high bandwidth network. So in this case, what you're seeing here is you can have, depending on your needs, you can have a hybrid network, where some of the sensors can be talking using LoRa, some of them can be talking using Wi-Fi, some of them can be talking using Bluetooth. Next slide. And in this case, for ours, we decided to use a hotspot, which is just the phone that we're using as our internet gateway. And then now I'll describe the idea of then the software-defined spectrum, like I said, where some of them can be talking in the 915 megahertz LoRa network, some of them can be using TV white space or Wi-Fi, others can be using Bluetooth, and then what you're bringing together is a hybrid network that fits the needs for the particular farm. Next slide. So now I'll show a quick demo of this idea of the software-defined spectrum for the software-defined farm. So suppose, let's say you have 200 devices you want to connect at the farm, then you can see how the network changes. And you can change the topology of the network into a star network where everything is beaming its data using one protocol. That's one configuration you could have. And then with the farm, let's say you have 4 base stations, but maybe you got more money now, you want to add a couple more base stations. So you have 6 base stations. You can see how the network density changes to meet this new configuration. And then for an average farm in the US, you have 450 acres is the average farm. But what if you had 4 acres, like you have a very small farmer who wants to deploy this technology? Then you can see how dense the network again changes depending on that. And what's important here is the hybrid network, where some of the nodes can be talking Wi-Fi in the 2.4 gigahertz, some of them can be talking Bluetooth, and then yet others can also be using LoRa. And with LoRa, you don't have just the bandwidth. There's a lot of factors you can change. You can change the spreading factor, you can change the bandwidth, you can change the data rate. So in this way, you're building a hybrid network to try to maximize your coverage. As you can see on the bottom left here, you have the device coverage for the 4-acre farm is about 100% coverage. So in this way, that's the idea of the software-defined spectrum for the software-defined farm. And I'll let Shang talk about the decision engine.
Right. So then now we can understand just broadly what does it look like for a typical 450-acre farm. And this is kind of just a brief visual of what that would look like. And then we can understand our set software-defined farm here at Cornell. And here we had 8 decisions which we had to understand to actually deploy this technology to have a full end-to-end system. And then now we can zoom in on just one decision. So for example, a farm sensor. Do you want to use a soil moisture sensor, a light intensity sensor, or do you want to use the novel micropotentiometer that we described just a little bit earlier, or a water stress sensor? These are all things that we need to understand when deploying this software-defined farm for each particular farmer or even in a research setting. And so now I'll kind of demo what this will look like for a particular farmer. And so when we understand these decisions, then we can computationally understand what might be the optimal set of decisions you should make for a particular farmer. And with that, we generate an entire trade space. Within the trade space, we understand those optimal ones, and we can actually download that to look at further analysis, and we can pull it up just shortly here to perform our own analysis to understand what has the high performance, cost, or risk for a subset of decisions. And then we can really understand each of these decisions in a very visual and interactive way through this graph, which you can pop up, and we see each of the decisions made and those subsequent returns for each of them. And then what's really important to filter based on a farmer's budget. So if a farmer only has X amount of dollars, then they can only afford a particular set of decisions, meaning a particular set of technologies that they can actually buy. And with that, we can understand also uncertainties within a system. So for example, if there is climate change or precipitation levels, those all impact a particular farm. So now we can understand that there's nine optimal policies that a farmer should make. And with that, we can understand also applying that on a graph that's interactive, I can play around with and understand the trade-offs between each of these. The next step now will be understanding these uncertainties in 1,000 states of the world. So in different states of the world, we can simulate what that will, how that will affect each particular policy. And we see here now that there's a large spread for each policy based on these different uncertainties within the world, again, such as climate change and the like. And with that, we can also understand different kind of policies paired against the other and understand what they look like and the trade-offs associated with each of them. So if we have a particular preference towards less risk or higher cost, we can do that. And that's our decision engine, which we're going through a little bit faster just for the sake of time. And so in summary, with our research, we've understood network connectivity, what might be the best network for your particular farm. We looked at the trade space to enumerate what the different architectures are for your particular farm based on your goals. And lastly, we visualized what this will look like for a particular farmer trying to use this type of technology.
So yeah, bringing together all of this work is, there's lots of excitement on where we can send it in terms of future research. There's some networking conferences, there's some human-computer interaction conferences, there's also some agriculture systems conferences, and that's where we're trying to take our work going into the future. And with that, we would like to thank you for your time, and we'll take some questions if you have any.
And brief disclaimer, we went really fast in the interest of time. There's a lot of interesting work here. Please ask us questions. If not, definitely contact us via email, and we'd be happy to share and collaborate. And if you guys are interested in kind of this FarmBeats work that Tushar just mentioned, we can also help out too, because we worked with them extensively this past summer to deploy that tech.
Thank you very much. Does anyone have any questions on their project or their research or where they're headed in the future? I will be posting their presentation online, so if you wanted to review their presentation, we'll have that available. It looks like, Phoebe, do you have a question? Phoebe, I think you're muted, but you have your hand up. I don't know if you have a question. Okay, any other questions for Shiang and Gloire? All right, thanks for your presentation today, and thanks to our other speakers. Really appreciate everybody jumping in and sharing the work that they're doing with FarmBeats. Next month,
Yes.
oh, sorry, go ahead. Yeah.
You did have a question, but she said that she couldn't unmute herself.
Oh no.
Let me see if I can unmute her. Hang on. The worst. Let's see. Or Phoebe, if you can do the chat, we can also try to read your question. It doesn't look like it's allowing me to unmute her, unfortunately. Oh, good idea. Maybe she'll type her question in chat. we can, there we go. There were 3 problems that farms face mentioned early in the presentation. Could you say at a high level how your approach is addressing these 3 problems? Cost, reliability, and scalability.
So I think both of us can answer this, but I think really the social science perspective of our research is how we're addressing them. One by Gloire's interviewing FarmBeats users, understanding how they're using the technology, but also for myself, I'm going forth with understanding the social science perspective of actually understanding what farmers need and what they want. So there's going to be a range of interviews that we are going to conduct with actual farmers to understand how the technology might help them and what they need for their particular farm, so that we can better shape our research for their needs.
So if I may answer, thank you for the social science perspective, Shang. If I may answer on the technical side, there's a lot of decisions to think about here. Some of them are the trade-off between where do you place the computation, for example. Do you place it in the cloud or at the edge? Like Tusher described, you might queue some of the messages until you have an internet connection. So it's how much data do you send to the cloud, because that's associated with cost. And it's also associated with reliability. Like it's all related in the technical side as well. And we're also trying to address those.
So I have a quick comment. So for the networking side of things, I'm guessing LoRa and having the white space and all these different modalities, that also has various cost ramifications, right? So when you're doing the software-defined networking, is that relatively straightforward to do? I'm guessing not, but I want to see what your response is.
Yes, you hit right on the money. And it's not that easy. The devil is always in the details is what I like to say. And yeah, we've done it once. Would hope that doing it more times will become easier, but now we're moving from LoRa to TV whitespace, and I'm sure that will bring its own challenges, because there's a lot of trade-offs between power consumption. There's trade-offs in like distance. So like there's bandwidth, cost, and distance that we have to think about. So then for some of our partners that are wanting to work with us, some of them might be better served by LoRa, some might be better served with TV whitespace, and then there's also real physical challenges you have to face here. Like Cornell, where we're located, is actually on a hill. So then if you place some nodes downhill or uphill, these are all factors that we have to deal with, and it's very hard to think about. And that's actually where my social science work is involved in. Like it's actually these material resistances that you have to deal with. That's where the good work happens. That's where like the future is created in how the limitations, how you navigate the limitations is how I'd like to phrase it.
And have people done this kind of work, related work, in terms of shifting between these different kinds of networking modalities, especially with TV whitespace? So I'm familiar with the OSDI, NSDI kind of forums. So I think it would be, I don't do too much of the networking stuff, but we have submitted stuff to Usenix, ADC, etc. Less related to networking and more related to performance modeling. So I'm wondering, what is the kind of related work you would cite for this kind of work? It sounds pretty novel and pretty translational, actually using this on a living test bed. So is this very novel in terms of introducing TV whitespace in the mix of the modalities?
Yeah, so I would like to pay respect to the original FarmBeats paper that they did use TV whitespace in that work as well. But what we're trying to do is, I guess, to take it to the next level, where you now bring different modalities and try to bring different types of hardware together and see how you can reconfigure the network. That's where the software-defined part of it is. There's the control plane and there's the data plane. You can set up the data plane, but it's reconfiguring to meet different needs. Like, let's say you're doing a biology problem, you have to reconfigure the network a different way. You're doing a dairy science problem, you have to reconfigure the network in a different way. It's what we're trying to take in. I think it's definitely novel, and we're really looking forward to doing the work.
Yeah, and then add NB-IoT to the mix, I guess, to make it even more complex.
Yeah.
Yeah, but very nice, very interesting work.
Thank you.
Right, any other questions? All right, well, we're right at 10 o'clock. I want to remind everybody that next month for February, we're moving back to our normal meeting day and time. The meeting's scheduled for February 25th, which is a Thursday at the same time of day, 9 o'clock Pacific, noon Eastern. If you have any suggestions for topics or things that you'd like to learn more about, feel free to send them my way. Or if you have some research that you're doing that you think the group would be interested in learning more about, reach out to me with that too, and we can get you set up to present at one of our future meetings. So thanks everyone. Happy 2021. I think we're all looking forward to having a good productive year this year. And thanks for joining today.
Thanks, guys. Bye.
Thank you, Stacy.
Thank you.
Thanks for having us.